In computer science, the Boolean satisfiability problem is the problem of determining if there exists an interpretation that satisfies a given Boolean formula. In other words, it asks whether the variables of a given Boolean formula can be consistently replaced by the values true or false in such a way that the formula evaluates to true. If this is the case, the formula is called satisfiable. On the other hand, if no such assignment exists, the function expressed by the formula is identically false for all possible variable assignments and the formula is unsatisfiable. For example, the formula A and not B is satisfiable because one can find the values A equals true and B equals false, which make equals true. In contrast, A and not A is unsatisfiable. SAT is one of the first problems that was proven to be NP-complete. This means that all problems in the complexity class NP, which includes a wide range of natural decision and optimization problems, are at most as difficult to solve as SAT. There is no known algorithm that efficiently solves SAT, and it is generally believed that no such algorithm exists, yet this belief has not been proven mathematically. And resolving the question whether SAT has an efficient algorithm is equivalent to the P versus NP problem, which is the most famous open problem in the theory of computing. Despite the fact that no algorithms are known that solve SAT efficiently, correctly, and for all possible input instances, many instances of SAT that occur in practice, such as in artificial intelligence, circuit design and automatic theorem proving, can actually be solved rather efficiently using heuristical SAT solvers. Such algorithms are not believed to be efficient on all SAT instances, but experimentally these algorithms tend to work well for many practical applications. Basic definitions and terminology. A propositional logic formula, also called Boolean expression, is built from variables, operators and or, not, and parentheses. A formula is said to be satisfiable if it can be made true by assigning appropriate logical values to its variables. The Boolean satisfiability problem is, given the formula, to check whether it is satisfiable. This decision problem is of central importance in various areas of computer science, including theoretical computer science, complexity theory, algorithmics, cryptography and artificial intelligence. There are several special cases of the Boolean satisfiability problem in which the formulas are required to have a particular structure. A literal is either a variable, then called positive literal, or the negation of a variable, then called negative literal. A clause is a disjunction of literals. A clause is called horn clause if it contains at most one positive literal. A formula is in conjunctive normal form if it is a conjunction of clauses. For example, x1 is a positive literal, x2 is a negative literal, x1 x2 is a clause, and x1 is a formula in conjunctive normal form. Its first and third clause are horn clauses, but its second clause is not. The formula is satisfiable, choosing x1 equals false, x2 equals false, and x3 arbitrarily, since false evaluates to true, and in turn to true true true. In contrast, the CNF formula A, consisting of two clauses of one literal, is unsatisfiable. Since for equals true and A equals false it evaluates to true true and false false, respectively. For some versions of the SAT problem, it is useful to define the notion of a generalized conjunctive normal form formula, viz. as a conjunction of arbitrarily many generalized clauses, the latter being of the form R for some Boolean operator R and literals Li. Different sets of allowed Boolean operators lead to different problem versions. As an example, R is a generalized clause, and RRR is a generalized conjunctive normal form. This formula is used below, with R being the ternary operator that is true just if exactly one of its arguments is. Using the laws of Boolean algebra, every propositional logic formula can be transformed into an equivalent conjunctive normal form, which may, however, be exponentially longer. For example, transforming the formula into conjunctive normal form yields While the former is a disjunction of n conjunctions of two variables, the latter consists of two n clauses of n variables. Complexity in restricted versions. Unrestricted satisfiability SAT was the first known NP-complete problem, as proved by Stephen Cook at the University of Toronto in 1971 and independently by Leonid Levin at the National Academy of Sciences in 1973. Until that time, the concept of an NP-complete problem did not even exist. The proof shows how every decision problem in the complexity class NP can be reduced to the SAT problem for CNF formulas, sometimes called CNF-SAT. A useful property of Cook's reduction is that it preserves the number of accepting answers. For example, deciding whether a given graph has a 3-coloring is another problem in NP, if a graph has 17 valid 3 colorings. The SAT formula produced by the Cook-Levin reduction will have 17 satisfying assignments. NP-completeness only refers to the runtime of the worst-case instances. Many of the instances that occur in practical applications can be solved much more quickly. See algorithms for solving SAT below. SAT is trivial if the formulas are restricted to those in disjunctive normal form, that is, they are disjunction of conjunctions of literals. Such a formula is indeed satisfiable if and only if at least one of its conjunctions is satisfiable, and a conjunction is satisfiable if and only if it does not contain both x and not x for some variable x. This can be checked in linear time. Furthermore, if they are restricted to being in full disjunctive normal form, in which every variable appears exactly once in every conjunction, they can be checked in constant time. But it can take exponential time and space to convert a general SAT problem to disjunctive normal form. For an example exchange, and, in the above exponential blow-up example for conjunctive normal forms, 3. Satisfiability. Like the satisfiability problem for arbitrary formulas, determining the satisfiability of a formula in conjunctive normal form where each clause is limited to at most 3 literals is NP-complete also. This problem is called 3 SAT, 3 CNF SAT, or 3 satisfiability. To reduce the unrestricted SAT problem to 3 SAT, transform each clause L1 lane to a conjunction of n-2 clauses, where x2, xn-2 are fresh variables not occurring elsewhere. Although the two formulas are not logically equivalent, they are equisatisfiable. The formula resulting from transforming all clauses is at most 3 times as long as its original, i.e., the length growth is polynomial. 3 SAT is one of CARP's 21 NP-complete problems, and it is used as a starting point for proving that other problems are also NP-hard. This is done by polynomial time reduction from 3 SAT to the other problem. An example of a problem where this method has been used is the clique problem. Given a CNF formula consisting of C clauses, the corresponding graph consists of a vertex for each literal, and an edge between each two non-contradicting literals from different clauses. Cf. Picture. The graph has a C-clique if and only if the formula is satisfiable. There is a simple randomized algorithm due to Schoening that runs in time n, where n is the number of variables in the 3 SAT proposition, and succeeds with high probability to correctly decide 3 SAT. The exponential time hypothesis asserts that no algorithm can solve 3 SAT in time that is fundamentally faster than expected. Selman, Mitchell, and Levesque give empirical data on the difficulty of randomly generated 3 SAT formulas, depending on their size parameters. Difficulty is measured in number recursive calls made by a DPLL algorithm. 3 satisfiability can be generalized to K satisfiability, when formulas in CNF are considered with each clause containing up to K literals. However, since for any k3, this problem can neither be easier than 3 SAT nor harder than SAT, and the latter two are NP-complete, so must be k-SAT. Some authors restrict k-SAT to CNF formulas with exactly k-literals. This doesn't lead to a different complexity class either, as each clause, L1, Lj, with j less than k literals can be padded with fixed dummy variables to L1, Lj dj plus 1, dk. After padding all clauses, 2k1 extra clauses have to be appended to ensure that only d1 equals dk equals false can lead to a satisfying assignment. Since k doesn't depend on the formula length, the extra clauses lead to a constant increase in length. For the same reason, it does not matter whether duplicate literals are allowed in clauses or not. Exactly 1-3 satisfiability. A variant of the 3 satisfiability problem is the 1-in-3 SAT. Given a conjunctive normal form, the problem is to determine whether there exists a truth assignment to the variables so that each clause has exactly one true literal. In contrast, ordinary 3 SAT requires that every clause has at least one true literal. Formally, a 1-in-3 SAT problem is given as a generalized conjunctive normal form with all generalized clauses using a ternary operator or that is true, just if exactly one of its arguments is. When all literals of a 1-in-3 SAT formula are positive, the satisfiability problem is called 1-in-3 positive 3 SAT. 1-in-3 SAT, together with its positive case, is listed as NP-complete problem, LO4, in the standard reference, Computers and Intractability. A Guide to the Theory of NP-completeness by Michael R. Gary and David S. Johnson. 1-in-3 SAT was proved to be NP-complete by Thomas J. Schaeffer as a special case of Schaeffers' dichotomy theorem, which asserts that any problem generalizing Boolean satisfiability in a certain way is either in the class P or is NP-complete. Schaeffer gives a construction allowing an easy polynomial time reduction from 3 SAT to 1-in-3 SAT. Let be a clause in a 3CNF formula. Add 6 fresh Boolean variables a, b, c, d, e, and f to be used to simulate this clause and no other. Then the formula RRRRR is satisfiable by some setting of the fresh variables if and only if at least one of x, y, or z is true. See picture. Thus any 3 SAT instance with n clauses and n variables may be converted into an equisatisfiable 1-in-3 SAT instance with 5 meters clauses and n plus 6 meters variables. Another reduction involves only 4 fresh variables and 3 clauses. RRR. See picture. 2 satisfiability. SAT is easier if the number of literals in a clause is limited to at most 2, in which case the problem is called 2 SAT. This problem can be solved in polynomial time, and in fact is complete for the complexity class Ni. If additionally all OR operations in literals are changed to XOR operations, the result is called exclusive or 2 satisfiability, which is a problem complete for the complexity class SL equals L. Horn satisfiability. The problem of deciding the satisfiability of a given conjunction of Horn clauses is called Horn satisfiability, or Horn SAT. It can be solved in polynomial time by a single step of the unit propagation algorithm, which produces the single minimal model of the set of Horn clauses. Horn satisfiability is P-complete. It can be seen as P's version of the Boolean satisfiability problem. Horn clauses are of interest because they are able to express implication of one variable from a set of other variables. Indeed, one such clause x1, xny can be rewritten as x1, xny, that is, if x1, xn are all true, then y needs to be true as well. A generalization of the class of Horn formulae is that of renameable Horn formulae, which is the set of formulae that can be placed in Horn form by replacing some variables with their respective negation. For example, x1 is not a Horn formula, but can be renamed to the Horn formula x1 by introducing y3 as negation of x3. In contrast, no renaming of x1 leads to a Horn formula. Checking the existence of such a replacement can be done in linear time. Therefore, the satisfiability of such formulae is in P, as it can be solved by first performing this replacement and then checking the satisfiability of the resulting Horn formula. XOR satisfiability. Another special case is the class of problems where each clause contains XOR rather than OR operators. This is in P, since an XOR sat formula can also be viewed as a system of linear equations mod 2, and can be solved in cubic time by Gaussian elimination. See the box for an example. This recast is based on the kinship between Boolean algebras and Boolean rings, and the fact that arithmetic modulo 2 forms a finite field. Since A XOR B XOR C evaluates to true if and only if exactly one or three members of A, B, C are true. Each solution of the 1 in 3 SAT problem for a given CNF formula is also a solution of the XOR 3 SAT problem, and in turn each solution of XOR 3 SAT is a solution of 3 SAT CF. Picture. As a consequence, for each CNF formula, it is possible to solve the XOR 3 SAT problem defined by the formula, and based on the result infer either that the 3 SAT problem is solvable or that the 1 in 3 SAT problem is unsolvable. Provided that the complexity classes P and NP are not equal, neither 2, nor Horn, nor XOR satisfiability is NP complete, unlike SAT. The assumption that P and NP are not equal is currently not proven. Schaeffers' dichotomy theorem. The restrictions above bound the considered formulae to be conjunctions of subformulae. Each restriction states a specific form for all subformulae. For example, only binary clauses can be subformulae in 2CNF. Schaeffers' dichotomy theorem states that, for any restriction to Boolean operators that can be used to form these subformulae, the corresponding satisfiability problem is in P or NP complete. The membership in P of the satisfiability of 2CNF, Horn, and XOR SAT formulae are special cases of this theorem. Extensions of SAT. An extension that has gained significant popularity since 2003 is satisfiability modulo theories that can enrich CNF formulas with linear constraints. Arrays, all different constraints, uninterpreted functions, etc. Such extensions typically remain NP-complete, but very efficient solvers are now available that can handle many such kinds of constraints. The satisfiability problem becomes more difficult if both for all and there exists quantifiers are allowed to bind the Boolean variables. An example of such an expression would be x, y, z. It is valid, since for all values of x and y, an appropriate value of z can be found, viz. z equals true if both x and y are false, and z equals false else. SAT itself uses only quantifiers. If only quantifiers are allowed instead, the so-called tautology problem is obtained, which is co-NP complete. If both quantifiers are allowed, the problem is called the quantified Boolean formula problem, which can be shown to be PSPACE complete. It is widely believed that PSPACE complete problems are strictly harder than any problem in NP, although this has not yet been proved. A number of variants deal with the number of variable assignments making the formula true. Ordinary SAT asks if there is at least one such assignment. Marge SAT, which asks if the majority of all assignments make the formula true, is complete for PP, a probabilistic class. The problem of how many variable assignments satisfy a formula, not a decision problem, is in #P. Unique SAT is the problem of determining whether a formula has exactly one assignment. It is complete for US. The complexity class describing problems solvable by a non-deterministic polynomial time Turing machine that accepts when there is exactly one non-deterministic accepting path and rejects otherwise. When the input is restricted to formulas having at most one satisfying assignment, the problem is called unambiguous SAT. A solving algorithm for unambiguous SAT is allowed to exhibit any behavior, including endless looping, on a formula having several satisfying assignments. Although this problem seems easier, Valiant and Vazirani have shown that if there is a practical algorithm to solve it, then all problems in NP can be solved just as easily. The maximum satisfiability problem, an FNP generalization of SAT, asks for the maximum number of clauses which can be satisfied by any assignment. It has efficient approximation algorithms, but is NP hard to solve exactly. Worse still, it is APX complete, meaning there is no polynomial time approximation scheme for this problem unless P equals NP. Other generalizations include satisfiability for first and second order logic, constraint satisfaction problems, 0 to 1 integer programming, self-reducibility. The SAT problem is self-reducible, that is, each algorithm which correctly answers if an instance of SAT is solvable can be used to find a satisfying assignment. First, the question is asked on the given formula phi. If the answer is no, the formula is unsatisfiable. Otherwise, the question is asked on the partly instantiated formula phi x1 equals true, i.e., phi with the first variable x1 replaced by true, and simplified accordingly. If the answer is yes, then x1 equals true, otherwise x1 equals false. Values of other variables can be found subsequently in the same way. In total, n+1 runs of the algorithm are required, where n is the number of distinct variables in phi. This property of self-reducibility is used in several theorems in complexity theory.